Hello and welcome to my talk on emulating hypervisors. My name is Aristeidis Thallas, and just like everybody else, you can call me Aris. Uh, First of all, a few words about me. I'm an electrical and computer engineer. I used to study robots academically. 3 years ago, I made a transition into security research, and since then, I work for Census. I'm mainly interested in vulnerability research, exploit development, reverse engineering, and so on. In my early steps, I used to break virtualization software, and now I'm mostly fighting Androids. So this is the main agenda of the talk. We're going to start with some introductory stuff about low-level ARM and virtualization extensions, and then proceed with our proposed solution and analysis of the target system, before continuing with discussing fuzzing implementations. So until recently, kernel used to be the last line of defense against a full system compromise. Of course, that's not true anymore since there are various mitigations that have been introduced. Hypervisors have been utilized as well, despite their traditional use for virtualization. In the Android ecosystem, this has been facilitated mainly by ARM virtualization extensions, and their main scope is to protect the kernel during runtime. That being said, debugging Android is a major pain in the ass, as most of you might know. There are endless customizations from various vendors and OEMs, lack of public source in many aspects, lack of public tools, the debugging interfaces. However, that being said, a proper debugging system framework is critical, and it's usually one of the most time-consuming tasks of researchers, and significantly improves the quality of work, the exploit development, and of course, vulnerability research. So, as Jonathan previously said, what most researchers end up doing is emulating targeted components under QEMU, which allows us full control over the emulated system. Of course, observability, including debugging. So in this presentation, we're going to talk about low-level ARM concepts and virtualization extensions. And we're going to demonstrate each concept introduced with a framework I implemented to bootstrap and interact with Samsung hypervisor called RKP. Under this setup, we're going to then investigate fuzzing setups, and hopefully this will allow you to understand the under examination system for you to build frameworks for your own systems. So first thing first, some things about ARM. Introductory stuff. There are two security states, secure and non-secure, also referred to as worlds. Four extension levels, also called execution levels. The higher the execution level number, the higher the privilege. So EL0 is the least privileged and is the user land. EL3 is the most privileged, and it's called secure monitor. To move between execution levels, we take interrupts, exceptions, or return from them. EL0 to go to EL1, we have a supervisor call, SVC instruction. EL1 to EL2, hypervisor call, HVC. EL1 or EL2 to go to EL3, we got a secure monitor call, SMC, and we drop to lower levels with exception return instruction, ERET. We're going to be targeting normal world EL2 in this talk. And what's EL2? It's a hypervisor, and its main thing is to dictate EL1 behavior and control it. We have mainly two things happening. First of all, a behavior controlled by hypervisor configuration register, which dictates the way EL1 interacts with the system. For example, we have the ability to trap access to system registers to EL2. So EL1 tries to access system registers, for example, to disable the MMU. The access is trapped to EL2, and he decides whether the action is supposed to happen or not, and different parameters of it. And then we have stage 2 translation, which breaks the traditional translation of virtual addresses. Without stage 2, each virtual address is translated via MMU to the corresponding physical address. And with stage 2, we have an additional step, as we're going to see next. So from left to right, we have the virtual address space of EL1, which is translated through stage 1 translation tables. And this is now an intermediate physical address, and this is what the operating system thinks is the actual physical address. But to retrieve the actual physical address, we go through stage 2 tables, which are not accessible by EL1. They are only accessible by EL2 and, of course, EL3. And more importantly, stage 2 tables and table entries have their own memory attributes, which ultimately define the memory translation process. For example, if a virtual address is defined as executable in stage 1 tables and not executable at stage 2 tables, then trying to execute from that virtual address results in a translation error. Samsung has implemented a security platform, which most of you might know is called Samsung Knox. As part of this implementation, they have a hypervisor, a proprietary hypervisor called Runtime Kernel Protection, RKP. RKP has been targeting before. There are various examples. The most notable one is is by Project Zero that targeted Samsung Galaxy S7 RKP implementation. In this talk, we will be focusing on S8, not 8 implementation, which shares some architectural similarities with the S7 one. It's newer with more additions and complexity. Moreover, it's been stripped and strings are obfuscated, making a reversing process more difficult. And one of the main reasons we chose this is that it's simple with respect to secondary functionalities and features. So it is a good target for educational purposes, but in the end of the day, it was an arbitrary selection. So now let's move on with the framework implementation and the analysis of the target system. We will be implementing a minimal framework, focusing components for EL3 and EL1 to allow to bootstrap and interact with EL2. Our framework is incorporated in an ELF 64-bit image, and since QEMU allows us to boot directly from ELF images, simplifying our boot process. Our starting physical address is hex 80 million, which is of great importance, and we're going to discuss later why. And then we have our configuration, which, as you can see, we use the virtual platform, Cortex A57 CPU, a single core with a single thread, 3 GB of RAM, and of course EL3 and EL2 enabled, and we attach to GDB. This is the actual command on the left. On the right, we attach the GDB, and we are now ready to start implementing our framework. This is a high-level approach of what we want to do. We want to start at EL3 and define our system state. Then we want to drop to EL1 and define its own state with MMU, etc. And then move on to EL2. This approach is not the only approach. We could do things. For example, we could drop from EL3 to EL2 and then move on to EL1. This is dictated from the targeted architecture, and there are differences. For example, if we have no dependencies from EL1 in the bootstrap process, then we can safely go to EL2 directly from EL3 and then drop to EL1. If we have dependencies, though, then, of course, we have to enable EL1 first. We're going to see how this is going to go for us. So system boots. So what we're going to do, first thing first, some simple stuff. We define the stack pointer so we can have local variables and invoke functions properly. And then we have to set the exception vectors. Their format is seen in the image next. There are 16 entries of hex 80 bytes each. They're organized in 4 groups of 4. Each group is used for a different execution level. And we have 1 entry for synchronous exception, 1 for interrupts, 1 for fast interrupts, and 1 for system errors. RKP does not support interrupts or fast interrupts, so we won't be enabling them. Excuse me. We won't be implementing userland applications on no EL0. As a result, EL1 entries are empty. Actually, they lead to infinite loops. And for EL3, we are only going to be supporting synchronous exceptions from lower 64-bit states, which is entry hex 400. After that has been said, we define the system state and some system registers. We will be focusing on EL3 and EL1 to allow RKP to define its own state properly, well, almost, as we're going to see next. So what we have to do, we boot reset EL3. We have to set the secure configuration register to define the world we are executing in. So we set a normal world. Define EL2 state as a 64-bit EL2 in the same system register. And we have to define EL1 state in the hypervisor configuration register. These values are required along with some reserved bits, and if we fail to set them properly, at least in the QEMU environment, we cannot drop to lower execution levels, as we're going to see next. So how do we drop to lower execution levels? We can only drop by returning from exceptions. Since we are at reset, there is no exception that led us there, so we create a fake exception to return to. And how do we do that? There are 3 registers which are related to exceptions. First, we have the exception link register, and this holds the return address after the exception has been handled. Saved process status register holds p-state, which is the state we were executing when the exception happened. And we set that at 64-bit EL1. Exception syndrome register holds information about the exception itself, and as a result, for returning is irrelevant. So after setting these values and executing instruction eWrite, we are now executing at EL1 at function, for example, start EL1 in this layout. So we have set our EL3 parameters, and we are now ready to start implementing and initializing EL1. Disclaimer, our setup is not identical to the Samsung Linux kernel. It's minimal in comparison, and we focus on bootstrapping and interacting with RKP. That being said, we have to stay as close as possible with respect to various parameters to the original kernel. For 2 main reasons. First of all, the nature of this implementation, in the nature of EL2 as a protector for the kernel, EL2 makes various assumptions and is tightly coupled with the kernel. So we must satisfy each of these dependencies for our setup to be correct. And even if the targeted EL2 had some flexibility regarding the supported systems, we must ensure that we are as close as possible to the under examination system to ensure that we have proper interaction and we study the proper behavior. So system registers for EL1, we extracted their values from source and the various oracles that are going to be introduced later. For now, we can assume that these are arbitrarily chosen. And one of the most important ones are TCR EL1, which defines the memory management setup. We specify 4 kilobyte page size, or granule size is the terminology, 512 gigabytes or 39-bit input virtual address region, and 1 terabyte intermediate physical address. So what this layout means is, first of all, we have 4 kilobyte page size, so 512 entries per page. And the 39-bit input virtual address region means that we do not require a level 0 table as we're going to see next. So this is how translations work. We're going to go backwards. Level 3 is the last table, and each entry here points to can map a 4 kilobyte page, of course. Since we have 512 entries, we can map a 2 megabyte region. Each entry is indexed, as we see from the image below, from virtual address bits 20 to 12. Each level 2 table, each entry indexed by bits 29 to 21, can either point to a level 3 table or to a 2 megabyte region, effectively ending the translation process. And how are these distinguished? The entry type is in the least significant bits of the entry. Block descriptors and page descriptors are more or less the same. However, page descriptors are only found in the level 3 table. So moving on, level 1 table indexed by bits 38 to 30 either points to level 2 table or 1 gigabyte region ending translation as well. So with a level 1 table, we can map 512 gigabyte region, and that's why we don't need a level 0 table. So for our ILIA1 implementation, we're going to be enabling the MMU. There are 2 page tables. We have one identity mapping for low virtual addresses, TTBR0, where virtual address is equal to physical addresses. And then we have the high virtual addresses for TTBR1, where the virtual address equals the physical address plus a prefixed offset, which you can see here. And we will be mapping our framework with level 2 block entries or 2 megabyte increments. So let's see how this works. We have created the page tables. We have not yet enabled the MMU. And this is the virtual address that we want to translate. This should lead us to the reset function. So we get the level 1 entry index, which is 2, and the entry for the second entry for TTBR1 is the one you see here. From the least significant bits, we can see that it is a valid page descriptor, table descriptor. So it leads to level 2. We extract the index for level 2 from the virtual address and read the entry from the second level table, which is now a valid block descriptor. So this means the page translation finished, and using the remaining bits from the virtual address and examining the resulting memory, we can see, of course, that we are in reset function. So that's how translation works. So we have enabled our MMU and set EL1 parameters. So we are now ready to bootstrap the hypervisor. The hypervisor in a framework is incorporated in the framework image, so it must be placed in its expected physical address. RKP is an ELF file, so we can easily figure out the physical address by reading the ELF header. Since HVC is not available yet, RKP has not been initialized, we cannot invoke HVC directly. So what we do is we go to EL3 and drop to EL2 in a similar fashion as we did for EL1. And to define the fake exception, we have the exception syndrome register, and we set there the ELF entry point, which is also available to us via the ELF header. Saved process status register, we specify 64-bit EL2 state, and as before, ESR is irrelevant. So returning, performing ERET instruction, we are now executing the entry point for RKP in EL2. The entry point eventually leads to VMM main. We can see an edited snippet here, and we're going to discuss the various steps next. So memory init is the first function of interest. It initializes a buffer, which is the first oracle. It is available to us via procfs entry RKP log, and we can see from the snippet that we have various memory regions, which allow us to verify that our configuration is correct and our process of bootstrapping is indeed similar to the original one. Next, we move to VMM init. There, the vectors are set, so we can now invoke HVC from EL1. However, we have to first enable the actual command from the secure configuration register. And finally, VMM init sets hypervisor configuration values. For example, EL1 writes to EL1 system registers are trapped to EL2. For example, RKP does not allow EL1 to disable its own MMU. Next, we have S1 enable and S2 enable. S1 is the stage 1 translation for EL2. We're not going to be focusing on that one. Stage 2 is really important for us. The page tables are statically defined, and the configuration for stage 2 is a 4 kilobyte granule size and a 40-bit input virtual address. And we also start at level 1 with concatenated tables. And this is very important for our analysis and to understand how things work. So in the traditional approach, we have 40 bits now, so we require a level 0 table with 2 entries indexed by bit 39, value 0 or 1. So we have 2 tables for level 1. Concatenated tables and ARM, what allows us to do is to reduce the translation steps, allows us to have 2 physical addresses, to physical pages in contiguous memory, which are indexed now by bits 30 to 39. So level 0 table is discarded, and we now have a 2-page table level 1. Of course, this is allowed for up to 16 concatenated tables. For example, if we had a 41-bit input virtual address region, then we would require 4 tables, which could be indexed by bits 30 to 40. And based on some other tools which you can find on references, we have built a tool to dump the tables and their memory attributes. So Hypervisor has been bootstrapped and terminates the bootstrap process. RKP terminates via SMC and effectively going from EL2 to EL3. X0 register, which is the first argument, holds a special value to let us know that it came from the bootstrap process, and X1, the second argument, has the initialization status. Since we perform an additional SMC, we now have an additional exception frame, so to continue from the previous state, we have to restore the exception frames. But since our framework is minimal, we do not require to preserve any information, so we can reset the state by dropping stack pointers and drop to a new EL1 function, which in our setup is the EL1 main. So a really important thing here is, of course, the first introduced system constraint of the physical address that we have to place our framework. Since stage 2 translation tables have been enabled, each virtual address, after being translated in EL1 by stage 1 tables, is not an actual physical address, but an intermediate physical address. And as such, it must be mapped in the stage 2 translation tables, or else we're going to have a translation fault. Examining the stage 2 tables, we can see that hex 80 million is executable, and that's where we place our framework. So we are now ready to start discussing the initialization of RKP, which is the second stage of the bootstrap process. But before that, let's talk about how exceptions are handled. All entries first create an exception frame and then lead to function VMM dispatch with 3 arguments. The first 2 are information about the exception nature, and the third is the exception frame. VMM dispatch only handles synchronous exceptions by design and returns otherwise. VMM synchronous handler is the handler for the synchronous exceptions, as the name suggests. And what happens here is pretty simple. We extract the reason for the exception, which is encoded in the exception class field of exception syndrome register. And HVC invocations, which are switch cases 12 and hex 12 and 16, are handled by function RKP main. To reach RKP main and the function switch case, we must satisfy some requirements for the command, which we're going to see next. First of all, the command is the first argument for HVC, x0, and must have a prefix, and it's the value that you see here. And this is checked before reaching RKP main. Secondly, in RKP main, as you see next, the command is shifted by 12 and a byte is extracted. So that byte is used as the index in the switch case. So before it's in the switch case, there's an additional function which we're going to examine here. But before discussing the function, let's see, for example, the second entry, which is RKP definite with ID 1. So how do we fix the command for this ID? We shift 1 by 12. So we got hex 1000 and OR with a prefix. So you can see right next the command that is required to be in x0 for us to reach RKP definite. Check HVC command function is RKP specific, and we're going to discuss it because it brings an interesting requirement that we need to have in mind for similar implementations. The command ID must be smaller than a specific counter, that's okay. And we have command counters, which are checked. Some commands are not allowed to be executed more than counter times. For example, the initialization commands must only be called once. If we somehow invoke them again, then system crashes. Other commands, for example, the third and the fourth entry with counter -1 can be called arbitrarily amount of times, of course. So now we can interact with RKP. Let's see how we initialize the hypervisor. The first function is RKP init with ID 0. You can also see the command. And it expects a struct with info about the kernel, such as the text and data regions, the vmalloc range, page table addresses, and some Samsung-specific regions. This is the function, and we're going to examine next the various steps. RKP debug log init initializes the second oracle, which is available via the same procfs entry, and on the top part of the snippet, we can see it being used and dumping system registers. And we can see the format of an edited snippet below. And this is really important for us because it holds information regarding several system registers which allow us to properly define the framework state. There are two modes that RKP can be executed in, and they depend on the magic value. Once RKP is initialized, with normal interaction, we cannot change the state. There's normal mode with magic value safe 1, and test mode with magic value safe 2. It enables testing, as the name suggests. And what does it do? Disable some command counters, so we can invoke some functions more than counter times, depending on the new configuration. And it enables a set of additional functions which are not defined without the test mode. The most important function of the RKP init is RKP paging init. It has various checks regarding the memory layout of the EL1 implementation. And our framework must satisfy each and every one of these requirements. Additionally, it edits memory region attributes for stage 2 translation regarding with respect to the provided memory layout. It sets internal information for memory region housekeeping. For example, it knows it can distinguish between kernel text region and a raw data region and specify and decide later whether a specific action is allowed or not. Unmaps sensitive regions from stage 2, so they are no more accessible from EL1. And each and every one of these steps must be successfully executed, or else RKP does not initialize, and we can no longer invoke HVC. This sample layout Some entries are not supported by functionality in our framework, for example, the vmalloc range. However, they are expected by RKP, and we must at least make sure to satisfy the region layouts for these memory regions. And also, the system constraint of 3 gigabytes is explained here, since it ensures that we have enough physical address to place specific regions in their expected physical locations. The second command is RKP deferred initialization, RKP definite with a command ID 1. It changes the kernel text region to read-only for stage 2 tables, so we cannot write the kernel text region anymore. And TTBR1 and its subtables are changed to read-only and not executable, as we can see from the snippet on the right. We're going to see those in detail in our demo. So we have reached a state where we can now interact with RKP and invoke further HVC commands. However, we did not follow the original initialization process to the letter. There are various routines that are void of meaning in our framework. For example, passing offsets for various kernel structs to RKP. For example, the credential structure, the Linux, VFS mount, and so forth. However, we did introduce the basic EL2 concepts we require to properly set a framework and interact with RKP. And the most important part is that we have reached a state where we can now interact and start investigating fuzzing setups. Before moving on, we must be aware of SMC invocations from EL2 implementations that lead to EL3. We have to handle them there, and this is mainly of importance both in the configuration stage, but also while fuzzing, because we can have unexpected results there, and fuzzers stop working. In RKP specifically, in this specific target, there is only one available, which is, it has its own HVC command and is related to verification of various images that are loaded from the disk, and we can leave that for now. So, safety first and demo. Okay, this is gonna be a live demo, starting the framework. All right, source. Okay, so we are at reset function. We start executing, and we reach a state where we are gonna drop to EL1. So SPCR holds the value to specify that we came from EL1, 64 bits. And we wanna drop to function start EL1. You can see the address here. SwitchL is a custom tool, so we can see we're executing on EL3 and then going further. Now we are at EL1, setting various registers, enabling the MMU. So we move back to EL3. This is the exception handler for EL3. It saves the exception frame and leads to handle interrupt, which is the main synchronous exception handler. So we move on to initializing RKP. Exception linked register is the ELF entry point. We specify that we came from an EL2 64-bit state in SPSR and continue. And this is now, we are now in the entry point for RKP, executing at EL2. This eventually leads to this function, which is VMM main, as we saw before. Continuing with our execution, we have now successfully bootstrapped the hypervisor. As we see, this is the magic value for X0, and 0 for EX1 indicates successful initialization. So we move on to EL3. System initialized properly, so we reset the state and drop to EL1. Okay, so first initialization function RKP init. So we can see here the expected values. We can see, for example, safe1 and the rest of the memory regions, which are passed to RKP. Invoking HVC leads to VMM dispatch. Next HVC command is RKP deferred initialization. This is the entry, as we saw before. So we create the exception frame in RKP, and these are the values that are passed to this function, which is VMM dispatch. Okay. I'm sorry, I didn't ask. Is this demo visible for everyone here? Do you want me to zoom in a bit? Good? Okay. So we have reached this function here, and we're going to demonstrate how useful our framework is. So this is going to change our text framework text region to read-only. So this is the value that we are interested in. Page walk, so we dump the tables. And we can see here that this is executable and read-write. So we execute this function, page walk again. So this was the initial state, and this is the next one. So the text region of the EL1 in our framework is now read-only. And this is a somewhat complex function. So with this framework, simply executing it, we can get an understanding of how things work before moving on to the actual auditing process. And this is similarly performed with TTBR1 and its subtables. Let's see that as well. So this is the value. We can see here its value. So now executing this function and dumping the tables again. This was the original value, and now we can see that it's not executable and read-only. So continuing, we also have access to the various debug buffers, of course. So the debug buffer and the log buffer can be easily accessed from our setup. And this is mostly it for now. Let's see an additional thing that's of importance. So let's say that we set our framework to be in a different physical address. Initialize the RKP, initialize here, initialization is successful. So we return to EL1, to EL3, initialize successfully. So we now try to execute, to drop to EL1. So reset the state. So this is the address that we now want to return to. And continuing from this point, we hit an exception in EL2, and the faulting address is the address that we wanted to return. So we wanted to return to an EL1 address that's not mapped in stage 2 tables, and that results in a translation error. Okay. So let's move on with the fuzzing setup. There are numerous approaches. For example, we could use ARM semi-hosting, which allows us to communicate with the host and uses I/O facilities, which is supported by QEMU and does not but we require to sync with the host somehow, and due to its implementation, it's probably going to be a bit slower. Or we can fuzz directly from QEMU, which is synced by design, but we must modify QEMU to support that. We chose the second approach for various reasons, mainly to study QEMU. So what we do is have QEMU create a test case and deliver that test case to the VM. To do that, we utilize break instruction. So we can pass commands from the immediate value. So instruction is BRK and immediate value. That value is encoded in exception syndrome register field instruction specific syndrome, ISS. So we can catch it in QEMU. And of course, we can create arbitrary fuzzing harnesses, but we must make sure that the test case created in QEMU and the framework that executes are in sync. This is how we handle break instruction in QEMU. It's ARM CPU do interrupt function. We get the exception reason from the field exception index, and we inject our functionality in hand BRK. We have created a simple harness to fuzz commands. So BRK moves on to QEMU. We get a random byte for the command ID, and we have an RKP specific thing. Most of HVC commands for RKP require a valid EL1 buffer. So we also satisfy that we copy random data to the buffer and feed that as a second argument. So after the test case is created, we invoke HVC and fuzz and then repeat. So this is how things work. After the initialization, we invoke break fuzz function, which we can see leads to BRK1. BRK1 is identified in QEMU via the syndrome. We have case 1. So we get a random byte. We create the command. This is the command ID. We create the command and store that in register X0. And then we have the EL1 buffer, and we copy random data into it and place its pointer to X1. So now we are ready to call RKP fuzz. Since QEMU makes sure to have the sync in set, for example, we have the command in X0 and the buffer in X1. We do not have to do further steps in the framework to sync the test case with the HVC invocations. So we now are ready to execute the fuzzer, and we do, and nothing happens. So what the hell's going on? There's nothing there to crash because this is a bare metal implementation. So what happens when things go south? Abort exceptions, which are synchronous exceptions. And what we do there, we handle them in QEMU. We identify them in ARM CPU do interrupt, same as BRK with the exception index. For example, here we have instruction abort and data abort. And in our function, we create a crash log and reset the QEMU to resume with the execution. This is a sample crash log, and we're going to see more details about it next. So don't worry about it. Before continuing, there are some special cases. They result in endless loop, and in our setup, that's disastrous. For this approach, the dummy fuzzing, we identify them via the address, but of course that does not scale well because we cannot know beforehand each single address that's going to lead to such a state. But there are more elegant solutions, for example, watchdog timers, but we are not interested in our dummy fuzzing to cover each and everything. For RKP specifically, there are two functions of interest, VMM panic, and this is found in only a handful of places. For example, if VMM synchronous handler somehow results in an error, for example, a synchronous exception that's not supported, then VMM dispatch leads to VMM panic. And what we do when we identify this is we reset the system. RKP policy violation function better aligns with the assertion logic. For example, if we invoke an HVC command more than counter times, then that leads to an RKP policy violation. So, conclusion. Oh no! Before the conclusions, let's see. A demo. It's not gonna be as fancy. So we are now executing policy violation, but we also have an abort. So that's good, something works. We can see here the abort in the host. Let's see the sample. This is SVE, as you can see here. This has been reported to Samsung. The slides do not have the sample because I was not sure if the patch would be public by then, by this time. So we can see the faulting address here. This is the command that resulted in the abort. So if you remember the command creation logic, then this is command ID hex 9b. And this is where the exception happened. We have also a disassembly here, so we can see that x0, x2 holds this value, which is controlled by us, and it is the guest buffer. And x0 has a predefined value, and it tries to access this address and write x1 into it. So in our crash log, we can add arbitrary information. So we have this for demonstration. These are the values for the abort. We have the CPU state, a disassembly to know where this happened, and memory dumps. For example, this is the fuzz data that is passed in the framework buffer. Okay, so this is gone. Right, so conclusions. So we introduced key concepts and discussed the various considerations we have to keep in mind when researching such targets, and some basic approaches to fuzzing. So hopefully with this information you can start developing your own frameworks. Some references and special thanks to people that contributed to my research. We can see someone here, or maybe this is a mythical beast. A teaser for you guys. I have also implemented AFL with full system QEMU emulation. Sadly, 50 minutes is not enough for everything. This was based on Triforce AFL, which is sadly abandoned. There are many changes since. These are the versions we used. So, as I've said before, for example, with the various situations that lead to endless loops, as you might know, AFL handles them with watchdog timers. That's why we don't care about them in our dummy fuzzing. This is a snapshot of the execution. We can see that we are executing at around 6,000 executions per second, and perfect stability, identifying new paths and crashes. So how are we on time? Not good. Okay. The demo for this one is not that fascinating either way. So that's it from me. Thank you all. So any questions for you guys? Let me show you this thingy here while moving to the questions.
Yep.
Okay, so we are executing the full system fuzzing. Oh yeah, go ahead.
Oh, nice work, Aris. Really
Thank
nice.
you.
Are SMC trapped by EL2? Are EL1 SMCs trapped by EL2?
For this configuration, I don't think so.
Yeah.
I'm not sure right now. You could probably do that, but I'm not certain.
I'm not sure it's that.
I cannot answer that.
Let's assume it's not for a moment. What would prevent EL1 from reinitializing EL2 by calling an initial SMC?
It depends on the RKP, on the EL2
Configuration.
functionality.
Yeah.
RKP has mitigations against this. It
Yeah.
has initialization status, which is set and cannot be reset.
Yeah, but
So
that goes through an HVC, right? That goes through, so the counters are only for HVCs. But the
It's
SMC,
irrelevant. If you have access to EL3, like code execution,
yeah.
then you don't care about EL2 because EL3 is higher in privilege.
No, correct.
But if you go to EL3 by SMC and then EL3 drops to EL2,
Yeah.
EL2 is already initialized and he knows that, or she.
So the EL3 is actually
EL2 knows
checking
that.
if EL2
Not
is
EL3, EL2. You could have EL3 do the check, it doesn't matter.
Yeah.
So long as someone has the check, but RKP knows that has that functionality in its implementation.
Let's discuss that offline. Let's discuss that offline. I'm interested. Thank you.
If something was not clear,
No, it's clear. I have other questions.
okay.
Any more questions? Any more questions?
All right. Are there any more questions? All right.
Okay,
I
let's
have
go
a final
then.
thing
Thank you.
for you guys. 2 minutes.
Sure.
I am really excited and proud to say that you can find further information in your favorite online magazine regarding this work. And I'm really proud to have contributed to FRAC. Cheers to FRAC staff. Cheers to FRAC staff for continuing to, for keeping FRAC alive with such amazing content, and for being very accommodating with my various requests. So, very proud to have contributed to their efforts. That's it from me. So feel free to reach out for any questions. I'm available. I'm gonna be here for a few days.